recording.
Okay, it's a pleasure to me to be the chairman today, and we 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 are here today to see the talk of Jianlu Zhang from the Academy of Mathematics and Science and System Science of the Chinese Academy of Science. And the title of the presentation is Oscillatory Orbits in the Restricted Planar Four-Body Problem. Then please mute the microphone and close the camera because the connection will be better if we do this. And in the final of the meeting today, Jai will talk some words about the platform chosen for today. Then it's a big pleasure to receive Zhang today, and let's see the talk.
Okay, thanks the organizers. First, I should say sorry because the network connection has the problem in Beijing because now the government is holding a national congress in Beijing, so it seems the network is not so smooth. Anyway, I was very appreciative with this chance to give a report on my recent work on the oscillatory orbit of restricted planar four-body problem. It's a joint work with the Tere Seara from the UPC Barcelona. Okay, let's see the background of the problem. First, let's review the n-body problem. Basically, we consider the gravitative equation just like this. The xi, I equals 1 to n. So basically, there are n particles. Each one, xi is the position, and we consider two different cases, R2 or R3. It represents the planar or the spatial cases. The mi is the corresponding mass, and G is the Newtonian constant. Basically, this equation can be created by the Hamiltonian function, just like this. Here, the pi is the momentum, and xi dot is the velocity. Apparently, we have the Hamiltonian ODE is a standard expression for the Hamiltonian ODE. And basically, for this problem, there are three cases different first integrals. The first is the center of the mass. Basically, is the sum of the mi times the xi, and also the momentum is the sum of the mi and the velocity times the velocity, and the angular momentum is the xi wedge product, the pi. So basically, these questions, the total dimension of the physics space is 2nd, but the previous first integrals can reduce the dimension by 3d plus 1. So the reduced dimension is 2n minus 3 times d minus 1. So we will consider the problem in the reduced physics space. Before we start the four-body problem, let's first review the three-body problem. Now there is the famous chassis classification. So basically, in the physics space, there is a singular set, which we denoted by S. It contains all the points corresponding to the double collision. So if we remove the singular set from the from the phase space, there are still some singular orbit, which is the collision orbit. That indicates in a forward or backward time, finite time, the orbit will turn to the singular set S. So in Alice's paper in 1968, he proposed the following conjecture, which he ascribed the credit to Siegel. The conjecture is that the set of collision orbit in the phase space are locally dense. So there is a previous work related with this conjecture is by Sari in 1970s. In 2 papers published in Transaction AMS, he got the following conclusion. For the restricted planar 3-body problem, the measure of collision orbit is 0. And another recent work by Guardia, Kalosha, and me in 2019, we get the following asymptotic result. For the RPC 3-body problem, here means the restricted planar circular 3-body problem, we restrict the mass individually by 1 minus mu and 0. Basically, the model can be interpreted as the Sun, Jupiter, and asteroid. There exists an open set U containing the R4, the 4-dimensional phase space, reduced phase space. This open set is independent of the mass of Jupiter, mu, such that the collision orbit are of the order mu to 1/20th dense in it. This is asymptotic estimate because here we need the mu be sufficiently small. So after we remove the singular set and collision orbit from the reduced phase space, all the part contains a regular set. It contains all the complete orbit, which implies the orbit exists for all the time. Based on the Chazis classification, we can separate the regular orbit into the following cases. It depends on the limit state of the orbit. So the first type is the hyperbolic. Here the plus and minus means the time limit. Plus is the forward time and the minus is the backward. So if the relative distance of the 3 bodies will tend to positive infinity, but the velocity tends to a positive number, is greater than 0, then we call such orbit be hyperbolic. Similarly, if we just change the velocity and let the limit be 0, then we get a parabolic orbit. If all the relative distance of the 3 masses are bounded for all the time, then we get the bounded orbit. So finally, there is a most erratic orbit, which we call the oscillatory orbit. That indicates the slope limit of the relative distance is infinite, but the infimum limit is bounded. That means the orbit will can be arbitrarily close to infinity and arbitrarily close to a certain bounded region in the phase space. So for n greater than 4 body, there are some more strange orbit comes out. There is the famous Pahlavi conjecture. which claims that there is a singular orbit which exists escaping to infinity in finite time. Here we also list two relevant works on this topic. The first is by Professor Xia about the five-body in 1992, and a recent result is by Professor Xue is on the four-body model. It's just published recently on 2020. So here I also borrowed some animation to illustrate the orbit of the three body. The first is about the famous figure 8, which discovered by Richard Montgomery and Alain Chansonnier. This model needs equal mass assumption. If we slightly change the mass of these three bodies and make them different, then we can get the following strange closed loop. Is still a periodic orbit, just like this. Sorry, but apparently these three masses doesn't lie on a same plane, and actually the orbit, the configuration they moved is rather strange. And also we can the two pictures on the right side also show that we can get other strange orbits for the three-body problems. And if we get we constrain some symmetry, we can get the following configurations. So now let's turn back to the oscillatory orbit. Here I list some historic works on this topic. The first I should mention is the Kolmogorov's conjecture is still announced in Alexeyev's paper. Basically, he claims that for the three-body problem, the measure of oscillatory orbits should be 0. And the first model we get the existence of the oscillatory orbit is the Sitnikov's model in 1959. It's for the restricted spatial three-body problem. Basically, there are two equal masses primaries moves on a plane, and there is a vertical axis across the center of the mass of the primaries, and there is a massless asteroid moves in the vertical axis. Basically, due to the gravitation of the primaries, the P3 will move up and down. So basically, if we restrict this model by adjusting a suitable eccentricity of the primaries, we can get some oscillatory orbits for the massless body. Then Seymour in 1980s, he got the for the planar circular three-body problem, he got the existence of the oscillatory orbit. But here he add an assumption that the mass of the Jupiter mu should be equal less than the exponential of minus g. G is the angular momentum of the massless asteroid. So the picture on the right shows the relative position of the restricted three bodies, the Sun, Jupiter, and the asteroid. After that, Professor Zhang published two papers in 1992 and 1993. he considered the RPC three-body problem or the RPE three-body problem. He proved the existence of the homoclinic orbit for all but some finite number of values of mu. Besides, he also give a sketch on the constructing oscillatory orbit in these two papers, or even the diffusion orbits is considered. Another work is the Guardia, Martin, Seara. He published a paper in 2016 on the invention mass. In this paper, just like the Seymour's paper, in this paper they consider the same RPC three-body problem, but he removed the assumption on the mass of Jupiter mu, but they need an additional assumption is that the angular momentum or the asteroid should be sufficiently large, but it's not exponentially large. It's just a posteriori given large angular momentum. There exists the oscillatory orbit. So another work is the Guardian, Martin, Seara, and Sabah on 2018. He considered the restricted the planar elliptic three-body problem. For this problem, he assumed that the eccentricity of the Sun between the Sun and Jupiter is exponentially small compared to the angular momentum. So for such a setting, they get the existence of the oscillatory orbit. So now we turn to our restricted planar four-body problem. For this model, we know that the primary is a three-body problem. So basically, for the three-body problem, intuitive idea is to consider the Km orbit for the primaries. If we get a Km quasi-periodic orbit for the three-body problem, then we add the massless four-body. Then we can literally consider this case. But for this setting, there are two difficulties have to be overcome. The first is that the KM method relies on the control of the motion of the primary has to be constrained in a certain form to get a nearly integrable structure. The second difficulty is that if the primary makes a quasi-periodic movement, then we need a high-dimensional lambda lemma to guarantee the existence of certain normally parabolic invariant cylinder. We will see that later. So, that's two difficulties stops us from consider this case. So instead we consider the following case. We let the primaries make a certain periodic orbits, but this kind of periodic orbit has some stability in the sense that if we vary the masses, it still persists. So such a periodic orbit helps us to find such invariant cylinder, and of which we can construct the oscillatory orbit. So this is our basic settings. We consider the Sun, Jupiter, Neptune, and asteroid model. The four model and the four masses, the relative distance is shown in this graph. Basically, the Hamiltonian now is of 2.5 degrees of freedom. Basically, the T here, since the primaries three-body problem makes a periodic motion, so basically this Hamiltonian is periodic OT also. And here the mass of the Neptune is delta. This is adjustable parameter, so we can adjust the delta to get a certain stability of this periodic orbit. And we should constrain that for the delta sufficiently small than mu, and we also let the mu equal less than a half. So the Jupiter, the mass of the Jupiter is less than the Sun, and for any delta belongs to the 0 to delta star, the periodic orbit is always close to a T delta periodic, nearly circular configuration. Here in this graph, I use the red dash to mark the relative circular position of the primaries. Basically, we can normalize the distance between the Sun and the Jupiter by 1, and let the Neptune comparably far from the Sun and the Jupiter. And here we involved a new variable epsilon, and let the distance be 1 over epsilon epsilon square. So the asteroid is moved close to a parabolic configuration. So that's the relative position for this model. Now let's state our main conclusions. The first conclusion is that for fixed mu belongs to 0 to 1/2, there exists an upper bound, delta 0. It depends only on mu, such that for any delta equal greater than 0, equal less than delta 0. Here, notice that the delta can be 0. If the delta equals 0, actually, the question will degenerate to a planar, restricted planar circular three-body problem, because there's no gravitation from the Neptune to the asteroid. Anyway, for this setting, for such a delta, the primaries indeed make a T delta periodic motion. Such a periodic orbit is called comet type in the book of Meyer, Hall, and Offen. A second conclusion is that for the aforementioned mu and delta, we can always find oscillatory orbit, but it's just the unilateral. It's not bilateral. So for the corresponding RP4 body problem. Here we will give a heuristic idea of the proof. The first step, we need to adapt sort of high-geometric rotating coordinate, and we suppose the distance between the Neptune and the Sun and Jupiter is of the order 1 over epsilon square, and let the epsilon sufficiently small. We proved that the existence of parameterized periodic orbit. Here there is underline. Here is implicit constraint we need to propose is that to avoid the collision between the asteroid and the Neptune, we can see that the asteroid is making nearly parabolic motions. So the closest point is on the horizontal axis. So if this distance is larger than 1 over epsilon square, there's no collision between the asteroid and the Neptune. So that will constrain the angular momentum of the asteroid. So we still need a exponentially small constraint of the delta. The delta should be exponentially small comparing to epsilon. Based on this assumption, now we can use the perturbative theory to get a normally parabolic invariant cylinder. So we briefly call it NPIC. So this cylinder is at the infinity. Basically, here we introduce the McGee's coordinate, and actually we transfer the equation in the region close to infinity and get a three-dimensional invariant manifold. This manifold is homogeneous in the sense that it consists of all periodic orbits, which are all the same. So basically, all the periodic motions on this cylinder are the same, or the same velocity and period. So finally, for the delta belongs to 0 to delta 0, we get a perturbative theorem of the RPC three-body problem. Here we know that delta 0 is sufficiently small. So when delta equals 0, we get exactly the RPC three-body problem. So we just get perturbative systems of this RPC three-body problem. For such a system, the transition chain helps us to get various orbital behaviors, for instance, the oscillatory and the diffusion. So the first ingredient is the Higgs-Meteor coordinate. Basically, we transferred the original equation from the Cartesian coordinate to the following rotating coordinate. Basically, the Q and the P is the relative distance between the Neptune to the center of the mass of Sun and Jupiter. So it's the relative distance. And for the Sun and Jupiter, we just consider the center of the mass and we introduce the polar coordinate. Here is R, capital R, omega. The capital omega is the angular momentum. Basically, we can find this Hamiltonian, the rotating Hamiltonian is of 3 degrees of freedom because the omega itself is first integral. So if we restrict the omega equals alpha, which also equals mu times 1 minus mu, then we can further apply the rescaling to the rotating Hamiltonian, which transfer it further into a rescaled Hamiltonian, just like this. Here, notice the P is the relative momentum of the Neptune. So basically, we know the mass of the Neptune is delta. So the P apparently equals delta times the V. V is the velocity. And we also get a rescaled R and capital R. So basically, the new systems becomes a decoupled system of the RPC three-body problem and a rotator. Also, there is a remainder part. The remainder part is of the order square root delta. So as the delta turns to 0, the remainder part will disappear. So basically, this system becomes a totally integrable. The second part is about the NPIC, the invariant cylinder. So under the polar coordinate, we know that the XA and YA is the Cartesian coordinate of the asteroid. can see from the original Hamiltonian for the four-body problem. So if we introduce the polar coordinate is the Kc, capital Kc, psi, capital psi, then we transfer the Kc, this is the radius, by 2 over x squared with a restriction x positive. Then we get the following equations. So apparently we can find for this equation in this coordinate, we can find invariant parabolic cylinder. Also, here we borrowed a parabolic invariant for the theorem discovered in the paper Guardia, Martin, Sabach, and Seara. We can find the stable and unstable manifold for this invariant cylinder, which are also C infinity smooth. So now we turn to the third ingredient, is about the transition chain. Here we should introduce a tool by the scattering map. The scattering map is a correspondence from the cylinder to cylinder. If one point is sent to another by the scattering map, that indicates they are connected by a certain heteroclinic orbit. So basically, as the delta is a parameter, now we can make a Taylor expansion with respect to the delta. So basically, we get the S0 plus delta times S1, then plus delta square order term. We know that for the RPC three-body problem, we get exactly the S0. This is a totally integrable twist map. The physical meaning of this S0 is that the angular momentum of the asteroid for the RPC three-body problem is conservative. So basically, for this case, we couldn't get some diffusion orbits. For delta sufficiently small, then the S delta becomes a nearly integrable setting because the S0 is an integrable twist map. So as long as the delta is sufficiently small, we can still apply the KM theorem to guarantee some invariant circle, the existence of certain invariant circle for the S delta. So basically, once we get such an invariant circle, that indicates we get an infinite transition chain by the scattering map, because it will send the scattering map will send any point on this invariant circle to this circle itself. So we can repeat for infinitely many times, and that will decide infinitely many parts of the scattering, the transition chains segments. Besides, we know that since the delta zero is sufficiently small and the invariant circle is compact on the invariant cylinder, so basically we can also find a uniform delta zero sufficiently small such that for any delta less than that, the stable manifold and the unstable manifold transversely intersect with each other along each heteroclinic orbits. So here is the graph for the shadowing mechanism to get a certain oscillatory orbit. Basically, we can see for each point on this cylinder, here the cylinders, since we can just draw the pictures on this plane. So basically we couldn't draw an entire cylinder. We just used a dot to represent any point on this cylinder. So basically for this point, the normally stable and unstable manifold will intersect with another point. If there is a heteroclinic orbit connecting these 2 points, then we can use the scattering map, send one point to another. Since now we have already get an invariant circle of the scattering map, so this bridge by the stable manifold and unstable manifold can be continued for infinitely many times. So we can start from the first point and choose a point. Here is the A, and the trajectories is marked in red. So it will send to the neighborhood of the second point due to the lambda lemma, because the stable manifold and unstable manifold is transversely intersectional to each other. So basically, use this strategy, we get a list of closed sets which are smaller and smaller. Then we take the intersect for all these sets. It's definitely non-empty. Basically, for such a starting point, we get a forward oscillatory orbit. Also, we can use the similar idea to get a backward, but it's not available to get a bilateral, because we couldn't get a two-sided intersection to guaranteeing the intersection of this set is now empty. Also, and last, I want to talk about a little bit about some heuristic idea to generalize the oscillatory orbit to the diffusion orbits. Basically, from the scattering map, if we can find a transition train such that the point make a very large variation of the angular momentum, then we can schedule this transition chain and get a certain shadowing orbit which also make a great change of angular momentum. Such an orbit is called diffusion. However, as we know that S delta is nearly integrable. So basically the KM theorem will stop the angular momentum to change make a great change. So the KM theorem constrains the variation of the angular momentum to the order square root delta, because this is the upper bound for two adjacent KM torus for the S delta. So that indicates by a single scattering map, we couldn't overcome this barrier to find such transition chain, make a O1 large chain variation of the angular momentum. However, for the restricted n+1 body problem, usually there are several scattering maps, because usually we can get several transversal heteroclinic orbits. Along each heteroclinic orbit, if the perturbative theorem applies, that indicates if we get in some sense if we get some nearly integrable structure. So basically we can combining these different scattering maps to get a composite transition chain. So for this composite transition chain, it still has chance to make a O1 large variation of angular momentum. So here is a work by Delshams, Kaloshin, Seara, and De La Rosa in 2017. He used some numerical assistance to prove that the diffuse Zhang orbit indeed exists for the RPE three-body problems. So thanks for the attention.
Thank you, Jianlu, for the great talk. And anyone have questions, comments? Hey guys, can you hear me?
Yeah.
My audio. If anyone has questions or comments,
Let me ask you a question. Its connection is not very good. Hello?
Hello?
Yeah, okay, so you're doing for four-body problem. Why not do just any n-body problem? That seems to be quite easy to do, right? The mechanism is there. To prove oscillatory solutions, all you need to do is find a Km torus for n-body problem, then put one zero mass at the infinity, and then you will get easy the oscillatory solutions. Why restrict to only four-body problem? Any number of bodies that's true.
Yes, that's a good question. So basically, the reason we consider four-body problem is that actually a straightforward method is to indeed consider the restricted n plus one body problem.
Right.
So the primary is the n-body problem. Apparently, there is a bunch of Km orbits for the primaries. Then and also this Km orbit is stable, but the problem is that it will lead to a complicated dynamics on the invariant cylinder. So we can see that the cylinder is here. If
right.
the primary makes a Km motions, basically this invariant cylinder is foliated by
right.
invariant quasi-periodic invariant torus, right?
Right.
So basically for this case, the problem is there is a difficulties because there is we lack actually a high dimensional lemma to guaranteeing the transversal intersection between the stable and the unstable manifold of the certain points on the cylinders. So apparently in the current settings, it's difficult to overcome. But I know that there is a group by Firoz, Martin, and Seara. They are considering this problem. So
why it doesn't work? For lambda lemma, just basically it's what Clark Robinson proved a long time ago. It's the same idea.
Yes, but actually the reason why we consider only four-body problem and we consider the periodic motion of the primary is that the cylinder here is homogeneous and it consists of the same periodic orbit. So basically, we can get actually Poincare map, which is send any point from this cylinder to itself. So basically, in certain under certain Poincare map, all the points on the cylinder becomes a fixed point. That's why we consider this case. Because for a fixed point, the lemma is still applied, the two-dimensional version. I mean.
But okay, so basically, the idea from Clark-Robinson's paper is that at infinity, these things it doesn't really matter that these perturbations are really small at infinity. So you have almost hyperbolic behavior. So the lambda lemma is the same as the stable manifold theorem. It's exactly the stable manifold theorem for a degenerate case. So the method there, it works. I mean, it doesn't really matter what type of motions that you have in the finite domain. And asymptotically at infinity, this is a hyperbolic. So therefore, you still have a stable manifold theorem. Once you have a stable manifold theorem at infinity, then you have lambda lemma. Once you have lambda lemma, then everything works, right?
I do believe that, but in the current paper, actually, we just need to make everything rigorous in a suitable length of the article. So basically, we didn't mention too much on the high dimensional extension. So, but that's a good question we can consider later.
These are something I did 30 years ago. I mean,
I know.
Basically, there's no the only kind of thing that one can improve is using variational approach. So if you if you use a variational approach, you don't need these kind of analysis. These type of analysis, you don't need a geometric analysis. Just go ahead, use a variational approach. You can prove for any n-body problem, not just a four-body problem.
Okay. I know. Actually, I read your papers, and it really inspired us greatly. So basically, in this work, we translate all these ideas in actually perturbative theorem language. So basically, we get current result.
Another thing is that you use variational approach. That's much better than using the geometric approach.
That's also a good question. But currently, the variation is not so helpful, and is because the systems has here the system. Sorry. Here. For in the rotating coordinate, the system is of 3 degrees of freedom, but it's indeed is positive definite. But there is a Coriolis force part. You can see it's here, right?
Right.
This term.
You put in the right setting.
The variational method couldn't overcome this term, so basically, that's a fatal difficulty.
Okay, all right. It's not using directly the variational method. You have locally along the stable.
Sure.
Use local variational method. Use local variational method. Don't do global because there's no global coordinates. And when you use rotating coordinate, that doesn't destroy the variational structure. Don't use rotational coordinates. Use local variational method.
If you restrict yourself on a local region close to the cylinder, I think
exactly. Because you're proving a local result. You don't have to use global variational method.
Yeah, sure. Thank you.
This is a general phenomenon, so therefore it should be true in any setting, and it doesn't matter it's a 3-body problem, 4-body problem, 5-body problem, and the oscillatory solution is just basically Snell's homokinetic theorem. When you have transversal homokinetic points, you have oscillatory solutions. So it's a very simple model. It's not complicated.
Yeah.
Can I ask you about the density you proved? The collision orbit density, what does that mean?
Okay, let me turn back to the problem. Basically, the configuration is more or less like this. So basically, the Sun, Jupiter, and the asteroid. The asteroid, the Sun and Jupiter makes the circular motion. So and we let the asteroid make elliptic motion, which the configuration just intersect with the Jupiter. You can see there are 2 intersectional points. So for such a configurations, we proved that in a certain region of the phase space, there's always densities sufficiently close to any regular orbit in the asymptotic estimate here. So we let the here the mu will turn to 0 and get a preciser estimate. You can see
what does that mean?
This site means that from any point in a small radius, from any point of this region, this set open set U, in the distance in a neighborhood of a radius mu to 1/20, we can always find a collision orbit, double collision.
Okay. That is just it's a fancy way of stating something not very.
It's also relies on the stability of these configurations, because whatever we vary the mass of the Jupiter, the configuration is still always has these 2 intersectional points. So
I see.
Also,
basically,
apply the TNE method here.
Okay, as mu goes to 0, so basically you can calculate.
The estimate will get better and better.
Thank you. Okay, I know what you mean. Okay, thank you.
Thank you, Jeff Shia, for the interesting discussion. And anyone have questions or comments? Anyone? Then thank you, Jianlu Zhang, for the interesting talk. And now we have some video.
Can I stop the screen now? Okay.
Yes.
Okay.
Thank you, Jianlu.
Thank you, Diego. Thank you, all the organizers again.
Then we have a video in honor for Hildeberto, and Annette will show the video.
Yeah, Marcelo, could you authorize me, please?
Jair, after the video, Jair will talk some words about the RNP platform and the Meet platform or Zoom platform. And after the video, Jair will talk.
It's without sound.
Sorry, I'm going to try again. I forgot to click the sound.